Hello, welcome to my talk on incompressible flows, streamlines, and stream function. In this talk, I will talk about the streamlines and the streamline equation by velocity vectors. Then we will see the stream function for the incompressible flows and the introduction for 2D stream functions, and then the properties of stream functions. At last, the relation between stream function and the potential function. In principle, a streamline is a line on which the fluid velocity vector is tangent to it everywhere. Suppose at a given instant t equaling to t0, we have the velocity vectors in the fluid field. We can either obtain this by numeric simulation or from the experiment measurement. Based on the definition of streamline, we can draw streamlines in the flow field, such as the dashed red line. We can see the velocity is tangent to the streamlines everywhere. Suppose at the instant t equaling to t0, we have a streamline as this, and then we can take a segment ds here, and the velocity at the segment would be tangent to this streamline. In mathematics, the equation for streamline would be given as the cross product of velocity vector v and the segment vector ds is 0. This equation means the velocity vector is tangent to the segment vector ds on the streamline. In the Cartesian coordinate, we can calculate the cross product of these two vectors. It is calculated as the determinant given as this. Here, the unit vectors I, j, and k are the unit vectors along x-axis, y-axis, and z-axis, and the velocity component u along x-axis, v along y-axis, and w along z-axis. And we have also the increment of the segment along x-axis, dx, dy along y-axis, and dz along z-axis. In details, the determinant would be calculated as this. So we can see this is the sphere vector. We have three components along x-axis here, along y-axis here, and along z-axis here. To make this vector to be 0, we must make all the components to be 0. Thus we have these three equations. And these three equations can be written as this. So the first equation comes to this, and the second equation comes to this, and the third equation comes to this. So we can see the position increment dx divided by the velocity component u would be same as the increment dy over the corresponding velocity component v. And the same as for the z direction dz divided by w, the velocity component on z-axis. Therefore, we can put all this together to make the streamline equation given as this. Here, the velocity component would be the function of x, y, and z. But the stream function is for the streamline an instant line at t0. Now we look at the expression for the streamline, that is, streaming function. As similar to the irrotational flow, where the assumption of the irrotational flow would lead to a scalar function, the velocity potential function. And for incompressible flows, given as the divergence of the velocity vector is 0, that means there exists a stream function vector psi such that the velocity vector can be calculated as the core of the stream function psi. Since this flow velocity vector would guarantee the condition of an incompressible flow, given as this, the divergence of the core of the stream function vector psi is 0. Since this is guaranteed, a divergence of a core of a vector is identically 0. This is equivalent to the divergence of the velocity vector is 0. Thus, the stream function and the relevant velocity vector v would guarantee the condition of an incompressible flow. Here we can calculate the core of the stream function in the Cartesian coordinate. The core of the stream function would be calculated given as this. Here again, the unit vectors I, j, k are the unit vectors along x-axis, y-axis, and z-axis respectively. And the partial differentiation with regard to x, with regard to y, and with regard to z. And the three stream function component, psi 1, psi 2, and psi 3. It is calculated as this in details. Three components along x-axis, this part, along y-axis, this part, and along z-axis, this part. So we can equaling the component of the velocity vector to the expression. So we have the expression for the velocity component u given as this, v is this, and w as this. So using the stream function, the velocity component can be calculated with the three components of the stream function vector, psi 1, psi 2, and psi 3. Obviously, if we compare the stream function to the potential function, which is a scalar function, but the stream function is a vector, that is, a stream function in 3D would have three independent components, psi 1, psi 2, and psi 3. So the application of the stream function vector to calculate the velocity vectors and the components would not provide much advantage in principle. In reality, the 3D stream function would hardly used and discussed. However, the stream function could be very useful in the 2D flows, and some of them are extremely useful. We will see in the following slide. In 2D flows, the stream function has only one component, written as stream function vector psi equaling to this. It's only one component, psi here. It must be noted there are not two components, only one component in the stream function vector. As such, the fluid velocity component can be calculated as we have done before. the velocity component u would be given by the stream function component. But in 2D case, psi2 would be 0. Therefore, we have the expression for velocity component u use the stream function component psi. Similarly, for the velocity component v, it is calculated as this, and psi1 is 0 in 2D case. Therefore, we have the expression for the velocity component u by the differentiation of psi with regard to x. And for your reference, the velocity component w would be calculated as this. And obviously, these two terms would be 0 since psi1 and psi2 are 0. So this velocity component along z-axis in 2D flows is identically 0. Thus, in the 2D incompressible flow, the velocity component u and v can be expressed by a scalar stream function psi. Thus, it can simplify the problem. One scalar stream function psi to represent two velocity component u and v, very similar to the scalar function, the velocity potential function for the three velocity component. Here we consider the 2D streamline equation, which is given as this: dx divided by u equaling to dy divided by v. So this can be written as this. If we substitute the definition of the velocity component into this equation, we have the expression as this. Here u is given as the partial differentiation of psi with regard to y, and minus v is the partial differentiation of psi with regard to x. So if we look at this expression, we can see this actually is the differential of the stream function psi, simply expressed as this. Thus, we can see on the streamline, the differential of the streamline would be 0. That is, on the streamline, the stream function is a constant. This is the reason why psi is called as stream function. And also, for different constant c, it would mean different streamlines. In this slide, we will look at the two different streamlines represented by two different stream functions, psi1 and psi2. See this plot, and then we will see what is actually the physical meaning of the difference of these two streamlines in the 2D flow field. From the plot, we can see the flow rate past the small element dl would be calculated dq equaling to v times dy, and minus v times dx, because in this plot v is in the opposite direction with y. If we substitute the expression of the velocity component by the stream function psi, we could have the expression as this, and this would be given as this. Again, we can see this actually is the differential of the stream function psi, simply expressed as this. So we integrate this expression, we can find the total flow rate between these two streamlines, psi1 and psi2, is equal to the difference of these two stream functions, psi2 minus psi1. Here, we can see in 2D flows, the flow rate between these two streamlines would be the difference of the two streamlines. However, this 2D flow rate must be understood as the flow rate of unit ways. Otherwise, the dimensions of this expression would not be correct. In here, for the 2D incompressible potential flows, we will see the streamline and the equal potential lines are orthogonal everywhere, since the dot product of the gradient of the potential function and the stream function is calculated as this. This part is the gradient of the potential function phi, and this part is the gradient of the stream function psi. And time this together, we can easily obtain the result as this. And use the velocity component. This, the partial differentiation of phi with regard to x is u, and the partial differentiation of psi with regard to x is minus v, and this would be v times u. So we can see this dot product of the gradient of the potential function and the stream function is identically 0. This means the streamlines and the equipotential lines are orthogonal everywhere. This is the nice plot for the equipotential lines and the streamlines for a doublet at the center of the plot. So the red arrows are the streamlines and the black lines are the equipotential line. From the plot, if we look at the cross of the equipotential lines and the streamlines, we can see everywhere they are orthogonal. Even these lines are curves, but we can see they are orthogonal. In the following slide, we will see an example, the very simple uniform flow. The uniform flow with the velocity u0 along the x-axis, and the flow velocity potential function can be expressed as phi equaling to u0x, and this potential function would be 0 at the origin of the coordinate, see here. And then we can calculate the velocity component u equaling to the partial differentiation of phi with regard to x. It is u0, and v is 0. So this velocity components are the constant velocity u0 or 0. So this is the uniform flow. And we can also calculate the velocity differentiation with x and y. Here, the partial differentiation of the velocity component u with regard to x, it is equivalent to the second order partial differentiation of velocity potential function phi with regard to x. It is 0. And the partial differentiation of v with regard to y is 0 too. Thus, we can see the uniform flow satisfies the Laplace equation. If we put these two terms together, you can see it is 0. And it is also satisfies the continuity equation. If we put this together, it is 0. In fact, Laplace equation is derived from the continuity equation. So satisfy one of the equation would satisfy another equation. Therefore, we can see the uniform flows are always incompressible, regardless of how large the velocity u0. even it is very large, larger than speed of sound, the uniform flow would be incompressible. Now, based on the velocity component u and v, we can build the equation for the stream function psi, given as this and this. And we can easily solve the stream function psi. It is equaling to u0y, and the stream function is 0 at the origin. Since we have already know the potential function and the stream function, so we can draw the equipotential lines. Since when x is taken a constant, the potential function would be constant. So if we take a different x, we would have different equipotential lines, the dashed lines. And for the streamlines, when y is taken as a constant, so the stream function would be a constant, which would correspond to a streamline. Thus, when we take a different y, we would have different stream function psi. So we have the streamline as the black arrows, see here. In here, we have looked at the 2D flow rate. This can be understood as the conventional flow rate of a unit waves. So when we consider the flow rate past the small segment dy here, the flow rate dq would be calculated as this u0, the velocity, times dy. And if we consider the expression for the velocity component and the stream function, we would have the expression as this. Here, u0 is replaced by the partial differentiation of psi with regard to y. And since psi is only dependent on y, so the partial differentiation with regard to y is same as the normal differentiation with regard to y. So this would be given as the differential of the stream function as d psi. So in 2D flows, we integrate this equation and we can get the total flow rate between two streamlines, psi 4 and psi 3. It would give the relation between this flow rate and the difference of the streamlines as this. Now in this slide, we will see the gradient of the potential function and the stream function. They are calculated as lambda phi, given as this. This is the gradient of the velocity potential function phi in 2D case. And this is the gradient of the stream function psi. In the uniform flow, the potential function is only depend on x. So the partial differentiation of the potential function with regard to y is 0. Thus, the gradient of the velocity potential function would be given as u0 times the unit vector I along x-axis. And for the gradient of stream function, since the stream function is only depend on y, so its partial differentiation with regard to x is 0. Therefore, we can also obtain the relation for the gradient of the stream function given as u0 times the unit vector j along y-axis. So if we time this together, the gradient of the potential function dot times the gradient of the stream function, it is given as this and this. And the unit vector I dot the unit vector j, because these two unit vectors are orthogonal, thus the dot product of these two vectors is 0. This simple example shows the equipotential lines and streamlines in 2D uniform flow are orthogonal everywhere in the flow field. See this plot. You can see the equipotential lines, the dashed lines, and the streamlines, the black arrows, are orthogonal everywhere.